It's a great pleasure for me today to introduce Rusbe for our Kent seminar. And Rusbe, let me just quickly give a quick introduction about Rusbe before he gets his presentation started. Rusbe, he did finish his PhD in Germany, Aachen. I think it's one of the biggest universities in Europe. In Germany, he does very good work on computational mechanics, especially. Correct me if I'm wrong, Rusbe. And then he worked with Continental for a while. This wasn't in his bio before he joined Michigan State University. So that's why he's really the right person who really can do something good about this computational modeling, the modeling of tires and its interaction with the pavements. And his work in Michigan State University as an assistant professor is primarily concentrated on modeling soft materials and also working on the relationship between tires and pavements and focusing on the multi-scale modeling of rubber and pavement texture interaction. And his talk today also is going to be about multi-scale modeling of the tire-pavement interaction to describe the role of pavement microtexture, something we usually ignore when you think about the effect of friction, rolling resistance, and when it comes to the microtexture effects of pavement on the tire itself. So let's give him a warm round of applause before he gets.
Thank you, Hassan, for inviting me, and thank you all for being here. Actually, attending this talk, which can be a little bit, let's say, off the topic for you guys in the pavement engineering. I try to actually manage it such that it fits your background better, but I am a theoretician in computational engineering, and my background is material science and mechanical engineering. So sometimes the terminology that I'm using is not exactly the same as what you are using, so please ask if something that I said doesn't make sense to you. This work that I'm actually presenting here will be in 5 parts. The first part, I describe what I'm looking at and why it's interesting for me. The second part, which is the main part of the talk today, is the rubber modeling. Then I talk about the surface modeling which has been done by a colleague of mine, Professor Chatti. And then the coupling, how we are going to actually couple these two models on each other, and the summary and the outlook of the project. This is an ongoing project. We are in the 3rd year of this project. I hope that we have 1 student and the 2nd student just started. We hope that we can expand this work. So I guess most of you are very familiar with the terms grip and rolling resistance. They are 2 basic performances that are basically sought after in the design of tires and the pavements. Grip is basically translated with the one-to-one term to the braking performance, and rolling resistance is correlated to the fuel consumption. Both of these terms, when we are talking about them, are actually consist of 3 mechanical phenomena. The first one is the hysteresis, or the energy dissipation through the rubber or the pavement. The second one is the adhesion between the tire and the pavement, and the third one is the shear stresses that you have on the contact surface. So the basically contribution of each of these terms are different based on the weather condition that you have on the pavement. Let's say for the case of snow friction or wet friction, for the snow you have a relatively high contribution of shear, but in the wet friction and dry friction, which basically describes most of the situation that we have, hysteresis play a major role in both of the terms. So, and hysteresis is basically what we are focusing on at this stage before moving on to include adhesion and shear. When you talk about the hysteresis, from my perspective, I mostly talk about the hysteresis in the tire. When we talk about the hysteresis in the tire, the general term, most of the work that has been done, is already about the energy that has been dissipated through the tire because of the deflection of the walls. When the tire wall actually hit the ground, the wall is actually deforms, and this deformation, this subsequent deformation in each cycle, creates a lot of loss of energy here, which we call it as a tire deflection. The second type of the hysteresis that we have is actually take place in the Meso-scale, and it's because of the combing effect that you have on the tire threads. The tire threads, when they hit the ground, they have a certain angle, and when they are actually want to get actually released from the loop, they have some sort of a snapback reaction where the tire thread are actually released from the pressure and it jumps back. This jumping back releases a subsequent amount of energy, and it's basically considering that during this time of the contact we are changing this angle. This is another sort of the hysteresis energy loss that we have. We call it the thread slip in the Meso-scale. On the micro scale, we have another type, which is if you look at one thread and if you look at the contact of that thread with the ground, then you have the thread deformation itself. This becomes particularly important because, as you know, in no point of the vehicle movement, the tire connection, the tire contact with the pavement becomes stationary. So basically, during all the movement, there is a constant slipping velocity here, which means that the tire constantly slides on the surface. Because of this, the tread pavement has a very high frequency deformation here. The scale that we call micro is from 20 micro to half a millimeter. Meso-scale is half a millimeter to 5 millimeter, and macro is 5 to 20 millimeters. So these are our definition of the scales. Knowing that, the main hypothesis that we have is that imagine that you have a rubber block and you want to slide on the surface. You have a semi-rough surface like this and you want to slide the rubber on that. Depend on the weight of the rubber or the pressure on the rubber and also the velocity of the rubber can penetrate into the certain types of asperities. It also, there were some type of asperities that remain untouched. The thing is that if you increase the speed, basically this deformation of the rubber is changing because the velocity of the rubber is changing. So rubber can see two different, let's say, type of roughnesses depending on the speed. In higher speed, it see a different roughness. In lower speed, it sees a different roughness. So it means that basically the grip and rolling resistance, if we talk about them in the lower speed and high speed context, they are actually sensitive to two different spectrums of the roughnesses on the surface. So the idea was recently motivated by an experimental result that has been done by a group in Sweden, that they actually have isolated a sample surface with the same macro roughness and two different micro roughnesses. And what they have found is that basically, despite the fact that the macro texture was the same in both samples, the surfaces show basically, depend on the surface, 25% to 50% changes in the rolling resistance only as the result of the different microtexture that they have. So our goal is to understand how we can capture the influence and the contribution of microtexture into these tire pavement interactions. A quick summary of what we have so far. We have basically, when we talk about the contact problems, we have two types of approaches. The first type of approaches are the tire models that we have basically started with a very simple sheet of rubber models to the very complex numerical finite element models to the full-scale tire models, which you have a tire built by including the wires, steel wires, steel fires, rim, shoulders, and all the details of the tire. These are one group of the model. The another group are the actually analytical models, like the contact models of the person as the, let's say, as the most prominent model on this role. And then you have single asperity, multi-asperity models, and the contact models, which are based on basically the local penetration. In both of these cases, what you have and what we have as missing is that the rubber is considered either linear elastic, in a better model it's considered hyperelastic, and in some better cases, we have linear viscoelastic. The reason that we don't go to a better models was that usually in these type of models, it becomes computationally very expensive if you want to actually use more complicated models. So our goal is actually to changing that and provide our model as a module that can be fitted into the full-scale simulation model. So we don't do the full-scale tire simulation. We provide a constitutive model that can be fitted into these models. So in this way, if you take a look at this contribution of the different scale, the hysteresis, we will focus on this scale and how we can analyze this scale. So the approach that we have is as follows. We try to actually provide a description for the mechanical properties of the rubber from the micro scale to the macro scale. The same thing for the surface. We try to actually provide a hierarchical multi-scale simulation of the surface, and then we try to actually impose them on different scales. Once we do that, basically we can provide a micro and meso-scale description of the energy dissipation in the contact. So to this end, we are starting with the rubber modeling. I just give you an overview why we think that rubber modeling is important. The rubber, if you consider it in the scale that you see in the tires, it can be considered as a continuum, okay? If you look at it in micro scale, not nano scale, micro scale, it's not a continuum anymore. So it should be actually considered as an inhomogeneous structure with the aggregates of the colloids, carbon black or silica, that are suspended between the polymers. This means that we are talking about two different nature of the material, continuum mechanics, and here you have the subcontinuum behavior, which is fundamentally different than the continuum behavior. And even in the tire, in the macro scale, what we have as a modeling is very simplistic. Let's see what I mean. Imagine that you have a piece of rubber and you want to load it in X direction, okay? This would be the behavior that you have. It's generally referred to as hyperelastic behavior. Then if you unload this material, what you see is that you have a certain type of damage that you can see in the first load. If you again reload this sample, you will see that the material gained back some of the energy that has been lost. So it's partial hardening, and then it follows the massacre after the previous loading. Another unloading, you will see the damage increases by the maximum load. Now take all these in inelastic phenomena into account. Now imagine that if we cut another sample in the y direction and stretch it in y direction, what happens? The interesting thing is that once you cut a sample in another direction, materials show anisotropy as well. So the behavior is this yellow one, and then if you do multiple cycles, this would be this. So imagine this behavior is actually simulated only by this dot line, which is the hyperelastic behavior, okay? And imagine that we want to actually consider the energy lost by the material. When we talk about the energy loss, if we consider the hyperelasticity, we basically do not include any type of the energy loss that are coming from the rubber itself. Okay? So the intrinsic energy loss inside the rubber, which is actually you can see as the difference between the loading and unloading, this area within the curve, has been lost in all the hyperelastic models. They are not included. And that is why the current hyperelastic models that we have, they don't give us any quantity. They don't give us any value that can be used. We use them only for ranking of different surfaces. So, knowing that, our goal is actually to understand how we can predict this and how we can build a model that, despite the fact that it can provide us with such a complexity, but also can provide us whenever we want, we can get rid of some of these inelastic phenomena and give us a more simpler type of description. In this way, our modeling range will start basically from the micro scale. We will rely on many molecular dynamics, quantum mechanics simulation that has been done by the others, or we start from the multibody dynamics, subcontinuum decomposition, and then we go on till end of continuum mechanics where we built a constitutive model for the FEM simulation. In this way, we have a model for the micro scale that actually influences the entire thread, and we have a model for the slip velocity or slip properties at the meso-scale. So our final goal would be to actually provide a material that can describe this behavior at this length scale, and at this length scale can describe the inhomogeneous stress distribution. So it starts with the following. We started with understanding how is the mechanics of these aggregates. It's basically, this is how we started actually to show formation of the aggregates. We once formed the aggregates with putting the particles and polymers together to form the aggregates. Once the aggregates are formed, we take them out and try to find out the properties between different particles. If we stretch different particles, then the stiffness are the same or not. Doing that, we can say if basically the clusters themselves are rigid entities or not, or if we can consider the clusters elastic or not. After this, we can take the clusters and stretch them and try to find a constitutive behavior for the clusters. Okay? Then, in the next step, once we have the constitutive behavior for those, we are working toward analytical modeling of the stress distribution within the clusters. Basically, what you have is that if you have the particles, a pack of particles that are, it's like the aggregates that you have in asphalt. Imagine there is no bin there. If you pack these aggregates together and you put pressure on them, the pressure is not actually, the stress is not distributed like a homogeneous material in a wave-like pattern. It will actually distributed like this. These lines that you see is the stress distribution. It's called the stress path. So the formation of a stress path is something very inhomogeneous in nature and describes the load transfer in subcontinuum level. Here, in aggregates is also like this. A backbone chain is created which transfer the loads inside the aggregates in the rubber. To understand that, to describe that, we actually decompose the aggregates into the chains. We take sections of the chain. We consider actually how the deformation would be. I spare you with the rest of the formulation. Just the very easy formulation to look at it is like that it's based on very simple logic. If you consider this a string of 4 particles, the energy of it is equal to the energy of torsion, bending, and stretch. Okay, so you have only three terms. So we just use these 3 terms to get the energy of this string, and then the rest is a simple formulation of how you can go from this string to the whole backbone and how you can go from the backbone to the cluster. It's basically a scaling up principal law, which is this one, and it's very simple. You have it from the multibody dynamics. Once you have that, you can have the strain energy of the backbone chain. In the subcontinuum decomposition, at the moment we have the energy of the backbone chain. In the subcontinuum decomposition, we have basically these clusters which are connected to each other through the polymer chains. And we want to see how we can understand and relate it to the mechanics of rubber itself, which has several inelastic phenomena. So to do that, the simplest approach is that let's imagine that there is 3 types of effects here. There is a elastic behavior, elastic with permanent damage, and elastic with cyclic damage. In this way, we can say that this material is a superposition of 3 networks. Okay, and each network is responsible for a specific type of behavior. For example, we say that if there are polymer chains alone, the material would have a hyperelastic behavior like this. Load, unload, reload would be all the same curve. Then we have a permanent damage. We describe it with this type of behavior. We say that, okay, there is a aggregates, and if they are stretched, the polymers are debounded from them, and this permanent detachment of the polymer is the result of this permanent damage that you have. For the cyclic damage, we talk about the temporary damage that we have in the clusters. So what we have is that, in essence, we try to describe what we see in the constitutive behavior as the result of certain phenomena in the structure. The good thing about that is that if we are right, if we identify the correct source of the damage, later on we can add the effect of different parameters easily to it. For example, the temperature is not included here. To add the temperature, all you need to know is that the temporary detachment of particles, how it is related to the temperature. And then automatically you have that here. So micromechanical modeling has this advantage that if you find out the mechanics correctly, finding out the resultant behavior is straightforward. Then having the mechanics of subcontinuum, basically the continuum mechanic would be the next step, and it's again very straightforward because you say that you have the mechanics of subcontinuum in one direction, okay? You put it you consider a representative volume element which includes all the direction, and you consider that in each direction you have a subcontinuum. In this way, you can discretize this basically representative volume elements into certain directions and do the integration here. So the energy of the representative volume element is then simply equal to the integration of the subcontinuum elements in all directions. To get rid of the integration, you can actually discretize it and do the numerical integration instead of the integration over the sphere. And then once you have that, you have the energy, the strain energy of the matrix based on the applied deformation and the internal history of the deformation that is applied to that material. So knowing that, consider the incompressibility condition and some normal procedure in the continuum mechanics, you can derive the energy of the stress of the continuum. This stress that you have will actually describe all the inelastic properties that we have previously described in different scales. So this would be the final product that we are actually offering in this project. So in this step for the rubber modeling. Our goal is actually to derive these with respect to different phenomena. So here we have it with respect to three phenomena as we have discussed before. This is the model prediction versus experiments. We have a sample, a stretch in x direction, then in y direction, and what you see is that the damage, the residual damage, the inelasticity, permanent damage, and then here is the cyclic damage is stretched once and then stretched the next time. This is actually the next time. So what I want to show is that basically the models show promising behavior, show good agreement with the experiments, and it's not a very expensive model. So it has the ability actually to be used in current simulations. So for the surface modeling, we have actually got a new piece of machine that can characterize the surfaces up to 2 microns. Once we have this, once we have actually cored the samples, we use the core samples to actually analyze and characterize the surface into certain waveforms. In this way, basically what we have the surface if you slice it in one-dimensional case, the surface profile would look like, for example, like this. We decompose it into certain wavelengths, and after detrending, we have for every wavelength a profile like this, right? So then we have the decomposition of these, and which will give you, for example, this as the composition of, for example, 10, 20, or a finite number of wavelengths. So once we have that, basically it's part that again comes to, because the characterization is actually not done by my group, it's done by my colleagues. Once we have that, the next part which comes to us again is very interesting, because if you have this wavelength decomposition, you can actually have a surface with the same macro roughness, but you can actually tweak the micro roughness, the micro texture, to have a high detail, low detail, medium detail, based on the wavelengths that you actually incorporate into the structure, right? So in this way, we can actually have 4 different, for example, surfaces with the same macro texture and different micro texture. Then the coupling would be, let's say, composed of 2 main steps. So as I said, the microscale is composed of 3 types of energy. So we have the energy dissipation of the tire, adhesion, and the shear. Then if we consider basically, if we, at the moment we cannot take into account shear, we are working on that, but at the moment we are in this scale. If we consider that for adhesive contact, we can actually cover the adhesive and non-adhesive contact. And for the adhesive contact, we have adhesion, hysteresis, and interlocking of the rubber with the surface. So this means that, for example, for the hysteresis itself, the coupling is the following. We have this full-scale rubber model, full-scale tire model, for example, coming from a tire company, or there are many actually research groups that have a full-scale tire simulation. We take from them, and then we implement our model at the thread scale. At this scale, we have a meso-scale rubber model, which is the model that I just presented, and we have a micro-scale rubber model, is the model of the aggregates, which will actually concurrently run on the penetration of the asperities into the thread tip here. So here we are talking about microns. In reality, if we talk about the energy that has been lost here, the energy is not much. But what you should consider is that the frequency that we are talking here about the deformation is something like 10 power 3. So it is a very, very high frequency deformation here. And because of this high frequency deformation, there is a subsequent heat production just on the surface of the thread, which is not propagated into the thread. In this way, we have a concurrent model at the meso-scale and the macro-scale, which should be run together. And then we add the adhesion by, we can actually use the current models. We have used actually implemented a current model from a group in Italy. So in Italy, and what we have is that the energy model can be added in the form of the strain energy. And once you have that, basically, we can actually calculate the rolling resistance with respect to certain asperities at different composition of the surfaces. So, so I have jumped basically quite much. No, let's talk about what's the benefit of the model. This is the part that I want to emphasize, basically. So the subroutine that we developed, this subroutine can be actually used and implemented in basically all the current full-scale tire simulations. So the tire simulations are have a simulation of the tire which has different entities inside. But for the rubber itself, the model that they are using are generally a simplistic one-scale model. So what we can have is that our code can be used as a subroutine inside the full-scale tire simulation or inside the multi-scale contact models and replace the current rubber model. And in this way, the tire becomes sensitive to micro-scale asperities. Okay? So, because imagine the case that you have right now, for example, we have right now, and we try to use linear viscoelastic material with the microasperities. What you get is basically quantitatively way off the real value, because when you have hyperelastic material in the microscale, first of all, you don't get the real heat dissipation that you have, because at that length scale, the material does not behave homogeneously. It's not a homogeneous material. The stress distribution is not homogeneous. And because of that, what you have, what you are simulating there is not a representation of a reality at all. The second thing that we can provide is that in using the microscale, with considering the contribution of the microscale, you can actually take into account the effect of the friction, grip, and rolling resistance, not as a terms, but basically all as the resulting factors that can be derived from the hysteresis of the tire and the hysteresis of the pavement. So these terms, these phenomena that we know at the macro scale, they are all translated into a simple micromechanical term of the energy dissipation at micro and meso scale. Another point that I can emphasize on is that the current simulation method, basically the one that we are proposing, can help us to see and validate many existing assumptions that are very popular in our field. For example, imagine the very assumption of linear relation between load and penetration. So in most of the models that we have, there is a assumption that if you apply a load on rubber, the amount of penetration that you have, imagine this rubber sheet, and this is your surface. The point is that if you apply load on rubber, the amount of contact area is actually linearly dependent with the load. So this is a general assumption. Now we have actually simulated a surface with the superposition of two wavelengths of 4 millimeter and 1 millimeter. What you see is that the surface area is almost linearly dependent, and that's true. So we can say in this case it's true. We just added a micro texture here, a wavelength, very small wavelength of 0.25 millimeter. In reality, it shouldn't have any effect on that. But what we see is that once you have that, the rubber penetration, specifically on when you slide the rubber, is changing dramatically. And that is because basically these small disparities that you see here, it takes time for rubber to actually deform itself from this shape to the shape after it. And so this 0.25 millimeter is a very high frequency wave. And that is why once you add that, this linear correlation that is actually widely popular in an assumption is not valid anymore. So now consider this assumption and now start sliding the rubber with a very limited speed. This is with very limited speed. What you see is that you have a dramatic decrease first in the amount of contact pavement, in the amount of contact surface, which is also true because from the stationary it becomes to the dynamic state, and then it almost keeps the same ratio. So again, the load contact, for example, the assumption of the linear load contact area relationship is something that you can, for example, easily check if you have a coherent model or a rigid model of the macrostructure and mesostructure. So in the next steps, we are looking forward actually to couple this model with a model of the surface, because at the moment we consider surfaces as rigid. In reality, what we have is that once the tire actually pushes onto the surface, in the microstructure, in the microscale and mesoscale, pavement deforms. The stress concentration at the tip of the aggregates on the pavement becomes so high that it pushes it down. Okay? In the macro scale, you can almost consider that the pavement almost remain rigid with respect to the tire, but this is not let's say this is not a rigid assumption when you go to the micro and meso scale, because these asperities that we see here, they are deforming once the stress concentration goes high, especially in the micro and meso-scale. The second thing is that we actually looking forward to have those coupled and implemented in a larger scale contact simulation, and then probably the field validation that can be validate the calculated values for the friction, rolling resistance, and grip. Thank you. That was it.
All right, now we have lots of time for questions.
Yeah.
Let me be better. Any questions for Rusbe? I can actually go with the first question. Maybe what people are still digesting and then preparing their questions, right? I can open the floor. So you said there are some measurements actually taken from different types of surfaces, right?
Yeah.
So those measurements, do you have any idea what are the differences between the microtexture? Because we usually, for example, if you're in this area, we usually use materials from similar geological sources. What kind of ranges are we talking about in the texture, microtexture differences?
So in their paper, they are consider anything below 1 millimeter as a this paper of Hoover here. They are consider anything below 0.5 millimeter as a micro scale, and they consider actually the two pavements with the same macro texture which is above 0.5 millimeter, and then their characterization for scales smaller than 0.5 millimeter. These two surfaces were very different. I don't know, but I think that maybe the aggregates have a sharp corners or something like that. I don't know how is the pavement could be different at that length scale, the material wise.
Pavement engineering terminology, usually microtexture, we talk about the aggregate surface texture, right? I don't know if you use it in the same context in your work. So that's probably what we would like to learn as well. So.
Yeah, so my microtexture is actually slightly different than yours, because I think in your terminology you consider anything less than 1 millimeter as a micro, right? If I'm not mistaken. Anything between smaller than 1 millimeter, you consider it as a microtexture.
Yeah, there is no good, index for that or reference for that. When all the work we did with the image analyzer, for example, you saw, right? When we looked at what is a typical surface texture value, what's an indentation on an aggregate surface? I mean, it's hard to find a reference on that. This is a very not well-established topic yet. And the way that you can quantify it by looking at, the roughest surface texture, for example, crushed stone versus, smooth gravel, right? That's how we can make that difference, and that's where we go. Basically.
Okay. Yeah. Then basically we are using different terminology, because in my terminology or in the tire side terminology, it's like that they consider micro anything that affects the head of the thread, this head of this thread. Okay, and it would be definitely what you have on the surface of the aggregate will actually affect this part as well. However, what you have also affects this part. So what you have as a micro scale in your case will be both micro scale and meso-scale here. But I don't have basically so in tire it's mostly like that. We say that in micro scale the rubber is not homogeneous material. So it's very clear mechanically. In meso-scale what we have is that the rubber is still a continuum, but you have a huge effect from the local sliding and high frequency loading. So.
Another question. Yeah. So you do, rubber block modeling, right? Dissipation. And how do you go from rubber to full-scale tire? How do you say that? Huh?
I don't go there. There are many people who are expert there and they have the model. I don't need to do that. What I need to do is just to give them the model. Is that when you have a full-scale tire simulation, you already built your FEM model. All you need is a subroutine for every continuum that you have. I give the continuum model. So what I have is a concurrent model for one continuum. You know what I'm saying? So my work is coupled with those. It's not replacing them.
But is there any work done, like even if it's maybe not very accurate, but to see the extent of, let's say, microtexture effect on rolling resistance or friction when it's really integrated to a full-scale tire rolling resistance or the grip effect?
No, and that's because even from the rubber society, which is in the material side, which is far more advanced, let's say, from rather than the structure side in comparison to them. Even in the material side community, multi-scale modeling and concurrent modeling is something new, and we don't have this model available even there, and we are publishing at that community at the moment. You know what I'm saying? So to have a solid comparison there, we need actually to couple it with a full-scale tire simulation. So we should finalize this and couple it with those. We have not done that. All we have at the moment is just the experimental test that has been published as a result of this Rosanna project in EU.
Okay.
That they have actually come up with some strong numbers for the effect of microtexture. I am not a pavement guy. I cannot actually talk about the validity of the test, but what they have published is suggesting a strong
The effect of texture on what?
microtexture on the friction and the rolling resistance. Yeah.
My question is regarding one of your last points. You mentioned that the next step is to consider the deformability of the surface.
Yes.
So my question is if you have an initial estimate of how inaccurate this model is, considering that the surface is made of asphalt concrete, which is a viscoelastic material, so there's some degree of dissipation there too.
That's true, and we don't consider it at the moment because I need a model from the pavement side which I can actually implement this on it. At the moment, I consider this rigid, okay? And so once I have that model, I can actually answer it. But at the moment, we don't have that, so we just consider it.
I guess my question is more like if you're aware of any estimation of how considering that effect of the deformability or the viscoelasticity of the surface itself is affecting the results of your model.
I think there are. I don't have any specific number in mind, but I think that there are many people who are working on the viscoelastic properties of the pavement itself, have rigid numbers that show that basically the pavement has a strong influence has a direct influence in the energy dissipation. Okay, but I don't know in this length scale. Seriously, we can actually talk about the viscoelastic energy dissipation of pavement, or more its effect is on the interlocking of the rubber. It's something I don't know. Yeah.
So the model right now is a block on top of the asperities, mainly on translational sliding, right?
Yes.
Would this model, or how would this model be able to handle the entry and the exit part, which has a lot, as you mentioned, a lot more frequency and dissipation compared to
How can it
middle?
handle what?
The entry and the exit, because it's not just translation, but a higher impact because the angular velocity is taking a role as well. How would this model take that?
So basically what we have here is not a rubber block. We can actually consider a rubber continuum. Okay? Once you have a rubber continuum, the loading type doesn't actually make a complication for you, because once we have a continuum, you can put it on any kind of deformation. So here, what you have when you actually enter this loading zone, this thread itself is decomposed into many continuums, many elements, and each of those elements have the behavior, the constitutive behavior that we have developed. So basically, because we can take into account any type of complicated deformation, we are not binded to a specific type of deformation. We are constitutive. We provide a constitutive model. Yeah?
Any questions? Other questions? I guess that's it.
Okay.
So much for the presentation.
Thank you. Thank you for having me.